Hello, everyone. Going to give you a brief update here of my presentation here. It's my project to generate regulatory cassette that we can use to edit the dystrophin gene in muscle stem cells. So what is the impact of skeletal muscle turnover on gene therapy, such as the AAV microdystrophin or even CRISPR treatments of adult muscle, where we deliver AAV vectors to restore dystrophin expression in these fibers to stabilize them? However, with time and during growth and maintenance of injury, there is a risk that there might be some turnover in these muscles that could lead to a gradual therapeutic loss. Now, if we could go in and edit muscle stem cells using AAV, we could correct the dystrophin mutation directly. Then those cells, in response to maintenance or injury, can fuse into those fibers and restore dystrophin expression. And this could be used in conjunction with gene replacement therapy or anything too. However, no safe and effective methods exist today to specifically target muscle stem cells, which is the goal of this project. Case in point, our most efficient genome editing approach for correcting dystrophin expression in skeletal muscle leads to this widespread muscle dystrophin expression in all the muscles that we look at, and with up to 40 to 80% of dystrophin being restored in these muscles. However, if we sort for satellite cells, and we analyze the dystrophin gene for mutation correction, we see that we have less than 0.01% correction using our CK8E regulatory cassette, which is not expected to be active in satellite cells. So we decided to go after this in two ways. Either go after resting or quiescent stem cells that express this gene PAX7, or go after active and proliferating stem cells that express PAX7 and MyoD. So we screened these genes for conserved regions that are enriched for myogenic transcription factor binding sites. And we came up with a series of different regulatory cassette candidates that we tested. These were added into a construct for a reporter gene and barcoded, and then packaged into AAV vectors, which we pooled and delivered into dystrophic and wild-type mice, from which after a certain period of time, we isolate the muscle stem cells and extract DNA and RNA to quantify the activity of these regulatory cassettes in relation to each other. We got some really promising results. First of all, we see that our AAV in this case was a myotropic AAV, that we could target between 15 to 20% of the satellite cells, and that we got some interesting, some good results here of some regulatory cassette candidates, both from the MyoD-based ones and also for the PAX7-based ones. Currently, we're moving ahead and we're analyzing these promising regulatory cassette candidates for actually editing the dystrophin gene in these mice. And future studies should consider developing more stronger and more dynamic regulatory cassettes that would enable both editing in existing muscle and stem cells, as well as to improve the delivery of genes to satellite cells. And this is the team that has been working on this over the past 2.5 years. And with that, I'd say thank you.